Okay, in this video I'm going to go over what's called the cylindrical shell method for finding the volume of revolution or the volume of an object of revolution. Okay, so the volume of an object of revolution. Okay, so let's start from the beginning, and let's say we have this curve, right, this graph of a function, and we want to define a region from A to B, bounded on top by this function f of x and bounded on the bottom by the x-axis. And so what we're going to do is, to set this up, we're going to partition again our interval into subintervals from x sub 0 to x sub 9, or excuse me, x sub n. And then we're going to choose a sample point, x sub I star, within each one of these subintervals. Okay? Now, where the cylindrical shell method comes from is we're going to define our rectangles, right? So we're going to make this rectangle, a small rectangle, with a width of delta x, right? And so what we're going to do is, let's define this part, this endpoint of this subinterval, right, is x I minus 1, and the endpoint, the right endpoint of the subinterval is going to be x sub I. Okay? Looks more like lambda. So x sub I. Now, the thing that makes this into the cylindrical shell method is we're doing our rectangles this way, right? And in the disk method, or the washer method, our rectangles were perpendicular to the axis of rotation. Now what we're going to do is, what if I want to have my rectangles go this way, but I want to rotate around the y-axis in this case, so now my rectangles are parallel to the axis of rotation. Okay, so now that's going to change some things. So let's see how this works. So if I take this rectangle and I rotate it around the y-axis, I'm going to get a cylinder, right? I'm going to get like a shell of a cylinder, right? And so how would I get the volume of this cylinder? Well, I'm going to, again, I need to find the volume of this rectangle. So this rectangle has an area, right? And if I rotate it around the x-axis, or the y-axis in this case, I've got to find the volume of this, I've got to take the cylinder, right, of the outside minus the cylinder of the inside, and that's going to give me my shell. So how do I do that? Well, what's the radius here? The radius is going to be x sub I. The height of my cylinder is based on f of x. Okay? And so let's take our point within here, our sample point, to find f x sub I star. Okay? And so let's find out what this is going to look like. Okay? So if I take the volume of the shell, right? So this is going to be the shell that's going to be rotated. So how is this going to look? It's going to be approximately, well, not approximately, it's going to be equal to f of x sub I star, oops, pi, we got to do pi because, again, we're rotating this around, And so if we look at the cross section of this, right? So look, the shell is a cylinder. So the volume is the cross-sectional area multiplied by the height of the cylinder. Okay? So the cross-sectional area, right? So the cross-sectional area is this. Okay? So the cross-sectional area times the height So let's visualize the cross-sectional area here. What is the cross-sectional area? Okay, again, the cross-sectional area is perpendicular to the axis of rotation. So in this case here, let me draw a picture. So we're looking down on the y-axis. And so here's our shell. There's the cross-sectional area of the shell. So what we need to do is we need to find this area. Right? So the cross-sectional area and then we're going to multiply that cross-sectional area by the height of the cylinder. Okay? So in this case, we've got an outer cylinder and an inner cylinder that we're going to subtract off, right, to get the shell. Okay? So that means we're going to take the cross-sectional area of the smaller, which is going to be the circle, right? And so we're going to have the inner circle minus the outer circle area, just like before. Okay? So when we look at our volume, or the cross-sectional area, it's going to be this, right? So the cross-sectional area is going to end up being what? Pi times x of I minus 1 squared. So that's going to be the inside one. So again, so we're looking down on it from here. And so when we rotate it, the cross-sectional area, x of I minus 1 is going to be the inside, and x of I is going to mark the outside. And so if we look at the radius of the inside one is going to be what? X of I. The radius of the inside cylinder is going to be what? The distance from the y-axis, which is x sub I minus 1. The distance to the outside, so the outside cylinder, right, the outside, the bigger cylinder, is going to have a cross-sectional area that has a radius of x of I. And so again, we're going to subtract areas of two circles. So that means it's going to be what? This. So that is going to be our cross-sectional area of the shell. This piece right in here. This. So we just found, looking down, this is the cross-sectional area. So it's like a washer again, right? But we're looking down. We're looking at the washer from a different perspective though. Okay? So we're not doing the washer method where we do the washer and we're rotating the washer around. Okay? Now what we're going to do is we found this shell, right? We found and of course the volume of this shell, right? So now the volume is going to be taking this cross-sectional area and multiplying it by the height. That's going to give us the volume of this shell that goes all the way around. So the volume of this one piece is going to be what? It's going to be pi times x of I minus 1 squared minus, oops, pi times x of I squared, okay, right? And then we're going to multiply this by the height, which is f of x, or f of x of I star. Okay, so that's going to be our volume formula based on what we're doing. So now let's take this a little further. Okay. So let's see where this takes us. Okay, so let's figure out how we can simplify this. So what I'm going to do is, let's start with this. So we got the picture. Okay, so make sure you draw this picture. And so what I'm going to do is, I'm going to erase this. And now what we're going to do is, we're going to see what happens to this as we simplify this further. Okay. So let's start with our volume formula that we just derived. And so it's going to be pi okay. Now, let's pull the pi out, and so we get x of I, x of I minus 1 squared minus x of I squared times f sub x of I star, our sample point, based on our sample point. And now this is a difference of 2 squares, so let's expand that out and see where that takes us. So we get x of I minus 1 plus x of I times x of I minus 1 minus x of I times that. Okay. Now, I'm going to rearrange, I'm going to pull this in front. So I'm going to write pi times f sub x plus sub I star. Now, this is just what? Look at your picture. This is delta x. Okay? And now, what I'm going to do is, I have the two endpoints, right? I'm taking the left endpoint plus the right endpoint. Well, here's what I'm going to do. I want to divide by 2, because if I divide this by 2, then I get the midpoint of the interval. But I can't just divide by 2 without multiplying by 2 as well, right? So I got to multiply by a fraction of 2 over 2. So let's add 2 over 2 to the mix. So I didn't change anything. All I did was just multiply by 1, right? So it doesn't change anything. So, but you'll see why I'm doing this. Okay, so now I'm going to pull the 2 out front. So I'm going to pull the numerator, the 2 in the numerator out front here, and I'm going to put the 2 in the denominator here. So I'm going to split it up, and I can do that. So 2 times pi times f of x of I star times x of I minus 1 plus x of I, all divided by 2 times delta x. Okay, so now, what is this? This is just the midpoint of the interval. And so since I can use any sample point I want, let's just make this x sub star, x sub I star. And so again, this is just a sample point, any point within the interval. So well, why don't we just make that the midpoint? Okay, now even though, here's the thing, even though the radius is a little bit bigger on the outside than it is on the outside, we can still do this, and as far as, again, we're going to be taking really small shells, right? Delta x is really small. So the difference between the outside radius and the inside radius is going to be negligible. So why don't we just take the difference, right? Or not the difference, but why don't we just take the average of the two and use the average? Because it's going to be so close, it's not going to matter, right? So let's do that. So now I'm going to define this as x sub I star. So now where does that take us? That takes us equal to 2 pi x sub I star times f of x sub I star delta x. Now, so far so good. What do we actually have here? Well, let's scoot back to the cylindrical shell. Let's say we have a Coke can, right? So let's say we have a Coke can that we cut off the top and the bottom, so we've got this cylindrical shell of a Coke can. And what if we cut up the side, right? And we unravel it. And we basically unroll the can after we cut up the side. Well, what are we going to get? This length is going to be what? It's going to be 2 pi x sub I star right? Oh, do I want to add that? Yeah, and then the height is f of x of x sub I star. And so delta x just measures the thickness, right? So delta x is if we add like a little thickness here, so the delta x would represent just the thickness of the shell. But again, as we go to integration, make integrals, we're going to basically take the limit as the number of subintervals goes to infinity. So that each subinterval is going to get smaller and smaller and smaller as we increase the number of subintervals on the interval from A to B, right? We only have this closed interval. So as we increase the number of subintervals, each subinterval is going to have a delta x, right? That's smaller. So this is going to 0, or in other words, it's going to go to dx, which is very infinitesimally small thickness, right? So, what is this formula? Remember, x sub I is the radius of the circle, right, from the cross-sectional. So this is 2 pi r. What is 2 pi r? That's the formula for circumference. The circumference of a circle times the height. So basically our formula, the cylindrical shell, is going to involve the formula for the surface, the circumference, times the height of the cylindrical shell. So basically we're going to take the circumference, right, of the shell. So let's say this is a shell, and what we're going to do is we're going to take increasingly smaller and smaller radii and basically fill in the hole with all of these shells. And basically take these little tiny volumes of shells, and we're basically going to fit smaller and smaller shells inside the larger shells until we have a full solid, a solid. And so it's going to be the same thing. So what are we going to do? Well, we're going to add sum of all of these shells. So our volume, right, so this is the volume of one shell. So that means that the volume of the solid of revolution is going to be the sum of all the shells from I equals, of all the shells from the sum intervals of I equals 1 to n of this, 2 pi x sub I times f sub x sub I delta x. And then of course, if we take the limit as n approaches infinity, well then this just becomes, so this would be an approximation, so the volume would equal the integral from a to b of 2 pi x times f of x dx. And that is the volume that we would get for using the cylindrical shell method. Okay, that's it. Again, if you have any questions, email me. Also, they go through this in the textbook, so you can review the textbook, but I'll be more happy to help you if you need any. So just let me know. Take care.